people who are responsible for public safety is what we're seeking here today. So without further ado, I'm going to introduce Richard Allen. Richard is a seismologist here at UC Berkeley with the Seismological Laboratory, and I think he's going to brief you on the remainder of the program for today. So welcome to Berkeley, and thank you very much, all of you, for coming.
Thanks. Well, thank you, Mark. I just want to make a few comments as well before we get started and sort of elaborate a little bit on some of the outcomes of the meeting that we had yesterday that Mark just mentioned. Before I do that, I just kind of want to sort of remind everybody of why we're actually talking about this here in Berkeley. The US, the entire west coast of the US is on a tectonic plate boundary, which you are probably fully aware of, and that means that we must be ready for big earthquakes here. Okay? What happened in Japan isn't an event that we should just think as a distant kind of occurrence. This is actually a possibility on the west coast of the US. This is a hazard map of the west coast. The color scale shows the ground shaking intensity. And then the black and red line here, this is the plate boundary that I'm referring to. This, of course, is the San Andreas fault system that runs up through California. At this point here, what we call the Mendocino Triple Junction, don't worry, there's not going to be too much of a geology summary here, just 2 slides. But this is the Mendocino Triple Junction, and just north of here is where we have a different tectonic environment. This is where we have subduction going on. And the point here is that the earthquake problem on the west coast is really divided into 2 types of earthquakes, the type that we have to be concerned about in the north, in the Pacific Northwest, and what we have to be concerned about here in California. To the north, it's the subduction zone that we have to think about, or partly it's the subduction zone we have to think about. The fact that we have one of these plates subducting beneath the entire west coast of North America. The largest earthquake that we're concerned about up in Cascadia is a magnitude 9. It's exactly the same as the event that we saw in Japan. It's on that kind of scale. So up in the Pacific Northwest, we have to be very concerned about these very large scale earthquakes and the tsunamis that are associated with them. There is also the threat of slightly smaller earthquakes, crustal scale earthquakes, but which are much closer to the cities. So, for example, directly beneath Seattle. In California, we have the San Andreas fault system, of course. The San Andreas fault system, the reason that you see this hazard as being a much broader zone is it's not just one fault, it's a whole series of faults that are subparallel to one another. And so the largest earthquake we would expect in California is a magnitude 8. So that's an order of magnitude less than what we expect in the Pacific Northwest. The difference is that those earthquakes are directly onshore, and so again much closer to the environments that we work and live in. And of course, I do want to sort of remind you, in case you need any more reason to be concerned about this particular problem, that one of the most hazardous faults in California is the Hayward Fault, and it's about 300 feet in that direction right now. So here at Berkeley, of course, we're very aware of the problem. Most famously, it runs directly across Cowles Memorial Stadium. So that's the earthquake problem that we face in the west coast of the US. Now, the event a few weeks ago in Japan was really a turning point in terms of geophysical networks. And the reason for that is that they delivered a warning to people before the strong ground shaking started. Japan has been working on a system for a number of years, and you're going to hear more about that later this morning. But the bottom line is that during this big earthquake, they actually were able to deliver a warning. So this is one of a very large number of videos that you can find on YouTube, where somebody in Tokyo started to get the warning. This is a pop-up display on his computer screen. It's showing the countdown until the shaking is going to start, and you'll see what happens in Tokyo.
Good.
So you thought that Mark's 20 seconds was an eternity. Obviously, there was actually significantly more time available in that particular example. So that's why we're here for these 2 days. As Mark mentioned, yesterday, essentially about 30 scientists from up and down the west coast of the US who are involved in real-time geophysical networks and monitoring systems gathered. And I just want to report very briefly to you some of the outcomes of that meeting. These are the institutions that were here yesterday, and some of those people are also here today as well. And obviously we spent a lot of time evaluating what happened in Japan, the warning system that they have in Japan, and also what we have been doing here in the US over the last few years. And I'm not going to read through all of these. I'm just going to summarize some of the bullets that we concluded at the end of the day. First is the warnings can be provided before earthquake shaking is felt. That's now a proven technology. There's no question about it. Warnings complement good buildings and planning. Earthquake early warning isn't a complete solution for the earthquake problem, obviously. It's an additional component that we can add to the approaches that we currently take. In the recent earthquake, a warning was successfully issued to the region that experienced the strongest shaking, the Tohoku region in Japan. At the same time, of course, we can identify areas that need improvement. In our conversation yesterday about how the system performed, it's very clear that there are some areas that need improvement. As I think many of you are aware, we have been undergoing a series of tests, development and testing of earthquake early warning methodologies for the West Coast over the last few years. And as part of that, we've started to engage with users, but now I think it's very clear to us that we're at the point where we really need much broader engagement of the possible user community. And of course, that is the primary reason that we are here today. And finally, in order to kind of really push this capability forward, we need to sustain and enhance the funding in order to actually do this. So that's the summary of what we did yesterday.